Good morrow, fellow humans. My name is Sean Crowley and I am obsessed with infinity. So join me as I attempt to unpick the infinities of what is. Most of us will have attempted to visualize our place within the universe at one time or another. But apart from humbling ourselves, what are the real benefits in doing this? And what are the potential uses of this understanding in relation to our understanding of self? What many of us fail to take into consideration when pondering this immensity of space is that our place within the universe is made up of far more than just a concept of where we are. The other thing we must consider is when we are, two sides of the coin needed before asking what we are. We can usually appreciate, on some level, the concept of infinite space. Personally, I find it much more difficult to imagine a finite reality. However, the idea that I now wish to begin dissecting is that a truly infinite reality must, by its nature, have the potential to be experienced from an infinite variety of perspectives. So let's start by dissecting the next most obvious dimension of perspective, time. Everything we've visualized thus far, regardless of its unimaginable grandeur, has merely been a snapshot, a single moment in time. And so if we continue to unpack the question, how, what we find is that even the briefest history of time will be enough to blow one's mind. But again, it's fun. In the beginning, or so they say, there was the before the before. This begat the singularity, which begat a silent and invisible bang, which begat space-time, the original Adam and Eve. Within the first measurable moment, being the time it would take a photon travelling at the speed of light to cross a distance of one Planck length, known as Planck time, everything that the universe is, was, and ever will be, was. And it expanded. At temperatures of 100 million degrees, 10 to the power of 32 degrees Celsius, it expanded, becoming all of space and time. An infinitely dense singularity, expanding infinitely into infinity. And as the infant universe expanded, temperatures rapidly dropped, falling more than 10 quadrillion degrees across the next 10 to minus 12 seconds to 10 to minus 6 seconds, as the first quarks, electrons, and neutrinos began to take their place on the universal stage. And by the time that the universe was a wholly ancient 1 second old, it had dropped another trillion degrees, allowing the quarks to slow, finding their equilibrium when, in a moment, they combined to form the first protons and neutrons. Across the next minutes of the universe's birthing, temperatures fell another billion degrees, allowing nuclear fusion to combine protons and neutrons, giving rise to the first nuclei of the first and simplest atoms, hydrogen, helium, and lithium. Until enough was finally enough, and at about the 20th minute, as universal temperatures passed their tipping point, nuclear fusion ceased. By which time, almost all hydrogen nuclei, being the most abundant element in the universe today, and making up not only 75% of matter in the universe, including dark matter, but also the very subatomic structures that create up to 10% of your own body right now, were already in their present-day form. Everything that is the you of now, the you of the past, and also the you of the future was, in one form or another, here. You were not only at the birth of the universe, you were the birth of the universe, and technically, you still are. But then, for the most part, it was done. The party was over, and the following thousands of years settled into a slow cooling as the sea of opaque radiation grew, in silence and in total darkness. And as the hot plasma soup cooled, it danced. For 240,000 years it danced, pitting photons against other charged electrons and nuclei, while still the universe grew. And stepping sprightly into its 300,000th year, with temperatures now as low as those found on the surface of the sun, electrons finally found themselves capable of being caught in the orbits of nuclei, allowing photons to travel freely across the then 45 million light-year stretch that was to become the observable universe that we see today. Meaning that for the first time since time, the universe was transparent. This began the first of the Dark Ages. There the adolescent universe sat, for 150 million years, in cold, quiet darkness, whilst gravity began its slow and deliberate game. Until one day, around 300 million years after the Big Bang, as the growing mists of simple atoms collapsed upon one another under the ever-growing influence of gravity, a remnant of the universe's younger self sprang back into life, as the first quasars converted the lifeless atomic sea back into hot, active plasma, thrusting it into life once again with the birth of light and the first stars. Supermassive blue giants. It's an amazing story, captured and written down by some of the greatest minds across all recorded history. But as beautiful as it may be, it, like our earlier topic of scale, well, it can be hard to wrap your head around. So in order to gain some perspective of how long time has been, let's reuse and expand upon a famous visualizing tool first popularized by Carl Sagan in his book Dragons of Eden, the Cosmic Calendar. The simple idea of the calendar is to condense the entire 13.8 billion year history of the universe, starting from the Big Bang through to the present day, into a single calendar year, with the Big Bang happening at midnight on the morning of January 1st, and the present day happening at midnight on the eve of December 31st. At this scale, 1 second represents roughly 437 years. 1 minute is 26,250 years. An hour is 1.5 million years. 1 day represents 38 million years. 1 month is 1.15 billion years, and the year obviously is the total 13.8 billion year age of the universe. Beautiful in its simplicity, it describes how everything described above, from the first Planck time to the birth of the first stars, all happened within the first week of the cosmic calendar. As the first stars continue to form and we pass into the second calendar week, glorious supernova explosions fuel an eternal reincarnating of the stars. And as these stars continue to die and be reborn, stellar families begin to cluster, growing ever in number until eventually they begin to form the very first galaxies on January 22nd. almost 1 billion years after the Big Bang. Our very own Milky Way galaxy didn't show up until the 16th of March, almost 2 billion years later. And our own star and solar system didn't form until much later, on the 2nd of September, 6.5 billion years later. Life on Earth began sometime after, on the 14th of September. However, multicellular life didn't take hold until the 5th of December, a mere 800 million years ago. Simple animals took to the waters on the 7th of December, with plants taking to land on December 20, 450 million years ago. The entirety of land-based life on Earth happened in the final week and a half of the cosmic calendar year. Dinosaurs take centre stage on December 25th, with mammals popping up the following day. The dinosaur die out at 6:24 a.m. on the 30th of December, and hominids appear at 2:24 p.m. on the very last day of the year. We domesticated fire at 11:44 p.m. and human history, beginning with the end of the last ice age, began only 27 seconds from the end of the year. The final second of the cosmic year represents all of modern history, stretching back 437.5 years. But what if we now continue into the future? How long can time go on ticking? Using the current most agreed upon theories, let us now move into the next year of the cosmic calendar, starting again at 12 a.m. January 1, now representing the current day. As we move into the future, it is true that the only definite will be change. Yet this is a change already breathing down the necks of our current generations, as they step up to the plate ready to face all that will be in the 21st century. Playing out over only the first 0.18 of a cosmic second, this century will force humanity to come to terms with many paradigm shifts, not least of which a population explosion that will continue to build towards 11 billion people by century's end, and which is already responsible for the 6th mass extinction of life on planet Earth, being the 3rd human-led extinction event to take place since our species stepped out of Africa. The likes of the current event, however, have not been seen since the decimation of biodiversity that occurred at the end of the dinosaurs' reign. And in this light, it's understandable how hard many of us find it to imagine our future in any positive light. However, during this turbulent period, we will also see many great achievements come to light. And if history is anything to go by, humanity thrives in the face of adversity. We will witness the first endeavour of private citizens journeying into space and the moon. And for the first time in the history of life on Earth, we will step on another planet. We will see the completion of the connectome, a digital mapping of the human brain, and this, combined with the exponential advances in computing, understandings of quantum mechanics and the capabilities of AI, we will see the first machines capable of processing data in ways that will surpass even the abilities of the human brain. Less than 2 cosmic minutes into the new year, Voyager 1 will have reached our neighbouring star Proxima Centauri, and at around 38 minutes, the Apollo 11 footprints will have finally faded from the surface of the moon. And if we survive into these following centuries, we will go on to witness the coming and going of islands, the flipping of Earth's magnetic poles, the changing of deserts into tropics and tropics into deserts, the ongoing shifting of continents and much, much more. And all this within the first hour of the cosmic calendar. January 2nd will see Mars gaining Saturn-like rings. And after about a working week lunchtime, the continents of Earth will have recombined into a new supercontinent, making all the lands of Earth one once more. During the first 2 weeks, regardless of humanity's influence, life on Earth will inevitably have to deal with a multitude of cataclysmic events. From supervolcanoes to asteroids, gamma-ray bursts, and even perhaps wandering stars. But regardless of these many battles and their eventual outcomes, by the end of January, with no say-so from the human race, all of Earth's oceans will have evaporated into space, leaving only the most resilient microorganisms to claim the planet as their own. So, yay for them, I guess. Well, at least until early March, when temperatures on Earth will soar beyond any point which life can now withstand. March. Life on Earth has until March. Now that might not seem very far away, but we must remember that in contrast, multicellular life had only come into being on the 5th of December of the previous year, so we still have plenty of time to mess things up. Yet, any interstellar travel or human evolution aside, it will still be a great shame as any future Earthlings will still miss out on the most beautiful of Earth's night skies, as the epic merging of the Andromeda Galaxy with our own Milky Way galaxy begins to take place in April of the new year. This dance of matter will continue to play out in our sky as Andromeda comes into view, growing slowly to fill the sky with all its coming and going of stars, planets and nebula, until it begins to warp the Milky Way around itself, and Andromeda's galactic core begins to dominate the night sky. When, in late June, our sun will begin its core collapse, causing solar temperatures to rise, forcing the sun to swell and expand into a red giant. As it continues to expand into the solar system, it will warp the orbit of our moon to a point where the moon will be literally ripped apart by the increasing gravity and its own celestial tidal forces, living for a brief period as the planetary rings of Earth, before crashing down onto the Earth's surface, as both Earth and Moon are engulfed, or at least singed, by the outermost perimeter of the engorged sun. By the end of June, any future civilization may find refuge further out in the solar system, as the habitable zone moves into the region of Mars's orbit, and then later towards Saturn's moon Titan. But any life left standing by August will watch as the sun begins to cool, losing half of its mass, shrinking down to the size of the Earth, entering its retirement age as a white dwarf. And this is how our nook of the playpen will sit at the end of the cosmic calendar year, when the universe is twice its current age, 27.6 billion years old, and still but a pup. Over the next 7 cosmic calendar years, as dark energy continues to prove ever victorious over the weaker effects of gravity, the very spaces between galaxies shall inflate until, like ships sailing into the sunset, galaxies are pushed over our cosmic horizon. Retreating in all directions at once, and at speeds which surpass the speed of light, these galaxies will remain forever out of sight, out of mind, and out of reach of any Milkdromeda residents. Only our nearby cluster of galaxies, known as the Laniakea supercluster, or the local group, will remain present in our skies. They, in contrast, will fall ever closer to one another, playing out a dance of immense beauty, lasting up until the 32nd cosmic calendar year, when they inevitably coalesce into a single, solitary Laniakea supergalaxy. And this is how things will remain: a sole galaxy, adrift in a seemingly endless sea of nothingness. The residents of this far-flung world will look to their skies and see no other galaxies, nor any record of their existence. Only now do we live in a moment of beauty and privilege that allows us to both know and learn of our origins. In our unique sliver of time, we are the lucky few. But here, in this far-flung future, is where things finally begin to slow. For as we reach the 72nd cosmic calendar year, 1 trillion real-time years from now, the once glorious stellar varieties of blues, whites, yellows, reds and oranges will begin to recede into the darkness, dwindling in number until eventually only the white dwarf cores of bygone stars and the slow-burning red dwarf stars remain. Our closest neighbouring star, that Voyager 1 passed in the 2nd minute of the 1st year, finally dies in the 290th calendar year. And by the 870th calendar year, all stars alive today will have completely faded into obscurity, but the era of starlight is still long from ended. It's not until the 7,246th calendar year that the stars will have fully depleted their reserves of hydrogen gas. And now, unable to regenerate, this final generation of stars will begin their swan song as the era of star formation comes to its close. By the 8,640th calendar year, 8,640 times the age of the universe today, even the slow-burning red dwarfs will have mostly retreated from view. To put this in some form of perspective, 8,640 years ago, humanity was making its transition from hunter-gatherer societies, inventing agriculture and becoming the first settlers. And yet by a thread, starlight continues to hold on. However, as we age into these autumn years of starlight, what we find is that our once magnanimous cosmic calendar is becoming too small to enable us to visualize the coming eons. So we do what we must and adjust the calendar's scale. From here on in, the 13.8 billion year marker that was originally represented by the entire cosmic year will now instead be represented by a mere cosmic second. Every single one of the 31,536,000 seconds to pass in this new calendar year will be equal to the whole of time from the Big Bang to our present day. And starting just 120 trillion real-time years in, from where we left the last generation of stars, it is now only 2:25 a.m, January 1st, of this new Omega cosmic calendar. All of time from the Big Bang to the beginning of the end of starlight has now been consolidated into just 2 hours and 25 minutes. So let us continue our trek into these following minutes, where, like the nightly winding down of house lights on a suburban street, the stars too continue to wink out, dimming the brightness of galaxies across the universe. By this time, most stars remaining will have shrunk from their engorged, volatile states and become non-active, slowly cooling, super-dense balls of matter that now only have the ability to shine out upon their many planetary worlds with a midday brightness equal to an Earth moon on a clear night. By the end of the first Omega cosmic calendar day, with this ever-failing influence of the stars, the planets begin to break free of their orbits, drifting freely into the great open void. And so it will come to be that as nuclear fusion winds down across the universe, light as a phenomenon will almost entirely come to an end. With no further energy left to give, the stars will work their way towards an ultimate resting state of iron, the ash of starlight. Inevitably, all that shall remain will be the skeletons of stars wandering the cosmos as black dwarfs. By mid-March of our Omega cosmic calendar, all galaxies, including our own Laniakea supergalaxy, will have ejected 90 to 99% of their contents into the wider reaches of space. Dead stars and planets and other drifting clouds of matter will be dispersed throughout the cosmos, only to be swept up by the ever-growing, ominous tenders of the darkness, the black holes. And here, in a universe where starlight has fallen beyond memory, the last safe houses of life will too be extinguished, as the symbiosis of life and starlight is lost to this universe and remembered by no one. Life and light, partners passing in the dark. And though no eye will ever see this freshly dark universe, it is still worth a moment of our recognition that we, in our far distant present, can still appreciate on some level both a beauty in its immensity and a wonder in its tenaciousness. Because though the universe may have returned to a state of cold darkness, the ageless shifting of universal energies will continue to remain undeterred. Playing out over a seemingly endless stretch of time, those wandering bodies lucky enough to evade the black holes will still come to an inevitable end. Slowly but surely, even these dead stars and planets will erode, coming apart from the inside out, as even their atoms, those created within the first few moments of the Big Bang, begin to dissolve into their simpler subatomic parts, dispersing their energies into a sea of free radiation. And now, as this degenerate era comes to a close, we find that even the unfathomable scale of our omega cosmic calendar, a calendar where every passing second was equal to all of time from the Big Bang to the present day, even this scale becomes utterly redundant. For the age required to envision the atomic evaporation of the black dwarfs requires not only months, years, or even centuries of our omega calendar. Sadly, this doesn't even come close. The time we seek to picture within our mind's eye stretches between an unimaginable 23 quadrillion and 23 sextillion omega cosmic calendar years. A real-time equivalent of 10 decillion to 10 duodecillion years. That's a 1 followed by 39 zeros. And as you can probably appreciate, from here on in, things become very hard to represent meaningfully with any commonplace scales of relevance. Because even if we were to grant ourselves another resetting of the calendar, it would still provide us with very little compensation. For example, let's just say that every second was to instead represent an entire omega cosmic calendar year. If this was the case, then though the period of time from the Big Bang to the end of starlight would fit within the first 0.23 milliseconds of this new grander year, this described evaporation of matter would still take as long as 730 trillion such years. But let's do it anyway. In vain though it may be, let us try to grasp at the inconceivable and place the unimaginable before our mind's eye once more. To do this, let us return to what we've already learnt, and now imagine a calendar so incomprehensibly massive that we could place our original cosmic calendar year within a single measurement of Planck time. That's the age of the universe, represented by 10 to the power of minus 43 seconds. At this scale, a full second represents a massive 1.38 septendecillion years. That's a 1 followed by 54 places. And the whole year represents an equally insane 43.5 novemdecillion years, 1 followed by 60 places. With this in mind, it's probably not surprising that our once prodigious story of starlight has now been reduced to a minuscule figure of only 73 undecillionths of a second, 73 by 10 to the power of minus 36. So, have we gone too far? I think that on first assessment, This would appear to be a completely reasonable conclusion, because at this scale, even the evaporation of matter, a story which was previously too large to be represented in any meaningful way, is now so minute that it too is now incomprehensible. That entire 10 duodecillion year long story would now only fill a tiny 73 nonillionths of a second. That's the entire story of matter, lost to inside a sliver of time so short that the blink of an eye would seem an eternity. So I hear you asking, why even bother? Because, dear listener, our story is still far from over. Now, take a breath as we move into the following trillionths of a second and watch as a sole survivor navigates the remains of this dying universe. Here in this new universal paradigm, our new lead protagonist is, of course, the wholly ancient sentience of the dark, our good old friends, the black holes. As the seconds, minutes, hours, days and months continue to pass in our new Planck calendar, the black holes take to the floor for matter's final dance. With large devouring small, ongoing into eternity, the black holes continue to dance across the infinite reaches of time and space. But all the while, as the dance moves forever onwards, the black holes are slowly starving to death. With no matter left to absorb, they slowly evaporate, radiating their enormous collections of mass into the timeless emptiness of open space, finally going the same way as all which came before. And though all songs must inevitably come to an end, theirs is not yet fully complete, for in their final act, as they draw upon their last reserves, and the speeds at which they radiate energy begin to compound, in that one last spectacular hurrah, they each explode in massive supernova blasts, calling back onto the stage for their final bow, a rare, brilliant flash of extraordinary light. And so as the very last black hole goes supernova, the final curtain will be pulled for both light and matter in the universe. And when all is finally over, all that will remain will be free-roaming photons and subatomic particles drifting carelessly across an unending cosmos. Welcome to the heat death of the universe. And so where is it that we've landed on our ludicrous Planck time cosmic calendar? Well, it's been suggested that at this scale, we shall not witness the universal heat death for, wait for it, another 2.3 septillion of our Planck time cosmic calendar years. So when you hear the phrase longer than anyone can imagine, this is exactly what they mean. What this is trying to represent is one Google in real-time years, the number 1 followed by 100 zeros. A number so large that there aren't even that many subatomic particles in the entire observable universe. And it must also be said that this is only the conservative estimate, because if it was to turn out that protons don't in fact decay in the way that we've just suggested, then estimates for an eventual heat death of the universe would skyrocket to figures in order of 100 trevectillion Google times that of the first estimation. Obviously, we can't imagine these scales of time, but they do, I feel, quite satisfactorily prove their point, that time is long, and the fragile spark of which we are currently a part is far more precious and rare than what many of us ever tend to consider. But time is a stubborn mistress, because there is absolutely no reason to think that time might find any reason for slowing now that the shifting energies of the universe have now subsided to only the subtlest of interactions, because even here, during the epoch of the photon age, change still occurs. Once all the black holes have eventually faded, those lost and lonely photons, neutrinos, electrons and positrons will continue to traverse the void, guided to what end nobody really knows. But much of what will follow depends on the underlying shape of the universe. Depending on whether the universe is flat, sphered, open or saddle-like, the universe could now either freeze, rip, bounce, fade, or even snap back into a crunch, none of which seem too pleasant really. But though there is fair reason to assume that this is the first time any of this has happened, there is equally sufficient reasoning to support the idea that this has happened many times, if not infinitely. The phenomena of quantum tunneling have led few scientists to suggest that the next Big Bang will in fact happen at a finite point somewhere in our far, far distant future. But when? How long must these subatomic particles drift before their states find the equilibrium required to flash an active universe back into life? Well, we've used our cosmic calendars to best describe the eternal play-out of the universe and its eventual heat death, which is due to occur in a Google real-time years, a 1 followed by 100 zeros. But there is a figure that is far greater, a Googleplex. A Googleplex is the number 1 followed by a Google zeros. And so the short answer to our question regarding the next Big Bang happens to be a mere Googleplex, 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 times our original suggested age of the universe at its heat death. Okay, we're done. Thank you so much for listening to the episode. I just wanted to offer a massive round of thanks and let you know that the conversation will be continuing both on our YouTube page and shortly on our Discord page. Many know that I've been researching this project for the last couple of years, and much of what will be presented over the coming series has been taken from the first draft of a manuscript that I've been working on, and I'd love to hear from you all just to learn what you liked, what you disliked, where you might think I'm wrong, where you might think I'm right, and basically just continue the conversation because, of course, discourse and community is what makes philosophy something that's living. So I'm very honoured to be sharing this process and this path and this journey with you. So I very much look forward to hearing from you all and continuing the journey together. Finally, the YouTube page is currently up and running, and that's giving weekly visualizations to the same readings that's happening in the podcast. So if you want to go over there and check that out, that is, again, Infinite Now with Sean Crowley. Head over there, look at the artwork that's being produced for that. A lot of work's gone into it, so hopefully I'll see you there week by week. Apart from that, good morrow, much love, and I hope you have a lovely day. See ya.